Okay, so we are at the top of the hour. Welcome, everyone. We're so glad that you decided to join us today. We'll be exploring water quality in the distribution system. My name is Lori Krings. I'll be moderating today. And our plan for today, we're going to kind of walk through a few announcements here. Okay, so just to let everybody know where we are hosting the webinar today from the Center for Technology and Training at Michigan Technological University in Houghton, Michigan. And we just have a few housekeeping things here so that if you have any questions, you can refer back to this one slide as we're going. Just a few key things for you to know. We'll be having some polls today. If you have trouble with your polls popping up, it could be you have a block up popped in Zoom. So consider that if you don't see the polls. And if you can't quite get that to work, you are welcome to put your poll answers right into the chat. We will be recording today's session. And then everyone's going to get a copy of that recording emailed to them when we send out the rest of the handouts, right? The slides and everything else that you might get to see today. We'll email that stuff to you when the certificates go out. Just keep in mind that that could take up to 10 business days for us to get that ready. We will be having a 5 or 10 minute break later on this afternoon, so you can plan around that. We will also be holding a question and answer period for the end of the session. So I will be monitoring that today. So if you have any questions, feel free to submit them either into the chat and I will hold them for later, or into the Q&A and I will hold them for later. It's up to you. And usually the main difference there is if you don't want everyone to see your question, you can put it into the Q&A part. Okay, and then just a note about the certificates. You will need to complete a SurveyMonkey link, which I will give you tomorrow at the end of day 2, if you do need a certificate of attendance. And we do have approval for Michigan CECs right now, and we're still waiting for the approval on the Maryland ones. And that usually just takes what it takes. So just know that that's pending. Okay, so that's really all that I have for announcements. Please, we welcome your questions again, and I'm going to go ahead and drop the slides for today into the chat, but do let me know if you have any questions otherwise. Welcome, everybody. And I'm going to turn it over to our speaker today, our first speaker, I should say, because we do have Greg Pearson with us today and Daryl Gotham. And I think, Greg, you're going to start off.
Yes, thank you, Lori. My audio is coming through okay?
You sound A-okay.
Okay, thank you, and welcome everyone. Today's topic, water quality in the distribution system. We're going to be looking at various topics that affect distribution system quality. And this is part of a nationwide project with a collaboration between all of the environmental finance center networks, which are, most of them are university-based, and they're all across the nation. Each region has at least one environmental finance center. And the Environmental Finance Center for Region 5 is located at Michigan Technological University, and our program is called the Great Lakes Environmental Infrastructure Program. And we provide training and technical assistance for small water and wastewater systems and tribal water and wastewater systems. And you can keep this slide for our contact information. The training and the technical assistance that we provide is at no cost for our systems. And I want to give a brief overview of the kind of topics that we're going to talk about, and then we'll look at the agenda, and I'll tell you a little bit more about what's going to happen today. So what kind of topics are going to be in this scope of water quality in the distribution system? The distribution system, as we know, it's separate from the treatment plant. However, it is affected by source water and by treatment as well. When we talk about the distribution system, we're talking about storage, mains, pumps, and possibly even wells in small groundwater systems. And we're concerned about protecting the water quality once it enters that distribution system from contamination. If we look at the various types of things that can happen in a distribution system, we can see that we can have things like excessive water age or nitrification in a storage tank. We can have problems at dead ends with disinfection byproduct formation, and also water age, loss of disinfection residual. In pipes, we can have challenges. We can have things like biofilm growing. We can have corrosion, leaching, and permeation in pipe materials. There's also the topic of cross connections and backflow that can affect distribution system water quality, but also we're affected by source water quality. And even treatment processes can affect downstream uh, water quality in the distribution system. We can have, for example, treatment can give us changes in pH and alkalinity, and different types of disinfection chemicals can affect water quality in the distribution system. Also, water age has a big effect on distribution water quality. And the kinds of things that we can look at is how long is water remaining in our storage tank? Do we have sufficient turnover? Are we flushing our system and uh, working to eliminate or manage dead end water mains? And the water quality in the distribution system is heavily affected by water age. You can see in this little graph on the top right of your screen that has water quality ages, and that bottom graph of time is in hours. And the performance index that different people in this study were looking at were things like disinfection, byproduct formation, loss of residual, and they were trying to figure out what's a good way to monitor the performance or the quality of the water over time. And you can see that over time, eventually, if you didn't do anything uh, to renew the disinfection residual or bring in new fresh water, that water quality would deteriorate. And it could be a number of hours or a number of days. And it depends on some factors that we'll cover today. And some factors associated with water age, loss of disinfection residual, disinfection byproduct formation, the growth of biofilms, and interactions with different types of pipe scales. We'll talk about that today. Uh, Increase in bacteria counts and development of pathogens, corrosion and tuberculation in pipes. And let me just move something here. Nitrification in tanks and dead end mains. And on this slide here, there's a link to that study that I was referencing where that graph comes from up above. And there's the link to that. You'll have that in your slides. Another issue is preventing the entry of contaminants. And there's a couple ways that contaminants can enter. It could be through some kind of cross connection where you either have back siphonage where there's a loss of system pressure, which either creates a suction or allows contaminants or unapproved water sources to enter the system, or you can have a situation where there's back pressure, where the customer has some kind of process like a boiler or pumps where the customer pressure exceeds the system pressure. And so both of those can lead to backflow. Another category, a wide category, is sanitary deficiencies, some kind of breach in the water system that allows contamination to enter. And a couple of examples would be you might have air release valves in the distribution system. And you see in this image here on the right of your screen, you have a screen inlet that allows air to be released or enter, and that would need to be protected from things like flooding or groundwater. Also, you could have something like a groundwater well that doesn't have an adequately sealed uh, casing at the top or an adequate sanitary seal, which could allow contamination to enter. There's also some factors with pipe materials. One issue is permeation, where contaminants like volatile organic compounds can pass right through the pipe wall. And this graph here is showing us the types of events or the types of chemicals that have been associated with over 100 events that have been studied by the EPA over the last couple decades. And most of them, you can see 89% were due to gasoline or gasoline products. Another issue is leaching, where leaching is the dissolution of metals in pipe materials, and things like linings and joints, where it allows those chemicals from the dissolution of those metals and solids to enter the water supply. And so that study where this image is from was from 1992. So they looked at 100 known permeation events at that time, and most were due to gasoline products from leaking storage tank or out and out spills. And one example is that they cited in this study was a simple 10-gallon gas tank leaked onto a roadway, and it permeated a PE pipe. And you can see the results here where it resulted in benzene, and if you look at the graph at the bottom, and toluene, which are components of gasoline products, to be uh, significantly over the MCL. And so it went right down through the ground and into that pipe. So if you want to look more into this topic, there's an excellent EPA manual called Permeation and Leaching. I've listed it here on this slide, and it's also in your references document. This would be in that references document that Lori will share later. There's some studies, but there's also some documents like this that are actual more like manuals. And I would advise you to save those either in PDF form or print them out and put them in a binder and add those to your water quality library. Also, anytime you're dealing with pipe materials or any kind of materials that come in contact with water, a good thing is to keep in mind the NSF 61 standard, which talks about drinking water system components that come in contact with water. Lastly, we'll be looking at operational practices, such as water main construction. And at the top table, in table 1, it's looking at the different kinds of issues that can occur when we either construct or repair water mains. So pathogenic contamination can occur under the microbiological issues column. And under the chemical issues column, you can see that the threats are chemical contamination, exposure to excess chlorine or loss of disinfectant residual, taste and odor and pH stability were also listed. And in table 2, they looked at the microbial quality of the trench water that was surrounding um, the main repair, and they found several instances where the trench water had positive test for total coliform, fecal coliform, and a couple other types of bacteria that I won't try to pronounce there, but those are associated with food poisoning type illnesses that will make people sick. So you can see that we need to have sanitary procedures when we install or repair water mains, because the surrounding water and soil can contaminate the distribution system. And just here's one example here of a fairly recent event that occurred in 1990. They had a main break, two major main breaks, and they repaired the pipe and flushed the pipe. They did not follow through with disinfecting the main, and it resulted in 240 cases of E. coli illness, and there was also 4 deaths. This happened in Missouri not that long ago. And if you look at this particular document at the bottom right of your screen, US EPA document called New and Repaired Water Mains, that is also a manual that would be worth printing out and adding to your library. Now, the things that we're going to cover today, we're going to begin. I'll continue this here a little bit to talk about water sources, quality, and some pathogens. Then I'm going to hand it over to Daryl Gotham, and you're in for a special treat today. Daryl's going to be talking about chlorine and disinfection byproducts, and Daryl is going to be teaching from the perspective of actually being in the past a regulator, working on the regulation side as a Eagle state of Michigan Eagle. Uh, I guess you'd call him a regulator, or he was working in the drinking water program. But he has also subsequently operated and managed water systems in a fairly large township in Michigan here. So Daryl can give you some perspectives from both sides of that. And then I'll finish up with some concepts about flushing, main repairs, and emergency disinfection. So we're going to continue on now and actually begin here talking about water sources, quality, and pathogens here. So first of all, groundwater sources. Groundwater is stored in underground aquifers, and there's basically two general types of aquifers. The most common is the sedimentary aquifer, where water is stored between uh, grains of unconsolidated materials such as sand or gravel. And you can also have a fractured bedrock well, where the water is stored in cracks in bedrock. And there's a term here to know, porosity. Porosity is the percentage of open space between those particles that can hold water. And groundwater, because it's in contact with these underground materials, particles of sand and rock and so forth, it has time to allow more minerals, such as calcium-based minerals, to dissolve into the water. So it's going to be higher in minerals, but it's going to be lower generally in organics because it's protected from surface water influences. When we look at aquifers, there's two general types of aquifers. There's unconfined aquifers. That's the higher aquifer here in this diagram. And that's subject to surface contamination. If something like a chemical spill occurs on the surface of the ground, it has the potential to percolate down into that unconfined aquifer. That unconfined aquifer can, if it has more recharge, it can rise. If it has pumping that's occurring, the surface of that unconfined aquifer will fall. So it can rise and fall. There's nothing confining it like in a confined aquifer. And in the confined aquifer, we have what's labeled as a confining unit in this diagram. That is usually a layer of rock or clay, and it protects that confined aquifer. And the water can't physically rise above that layer. Um, but because of the recharge area being higher uh, than where you're pumping, usually you'll have some pressure called artesian pressure on that well. And the image kind of right to the center left of that image, you see the flowing artesian well with that pressure. Like if you held up two ends of a hose and lowered one in, water would come out. The same concept. There's the recharge area has a water table that's higher than the top of that well casing, so it's able to flow. But it doesn't have to actually flow to be artesian. It just has to rise higher in the casing. And so confined aquifers are a little more protected. And if we had some contamination on the surface, it could possibly percolate down right into that unconfined aquifer. But you notice it goes right by that flowing artesian well that's drilled into the lower confined aquifer, and it's not making its way through that confining layer. In a surface water source, you have the concept of a watershed, and eventually all this water quality makes its way, if it's not removed in treatment, makes its way to the distribution system. That's why we're talking about this. So this is a situation where the water is much exposed to a much greater degree to contamination that occurs on the surface. As you uh, look at a watershed, you're looking at where the water comes from, where it runs off to enter that particular water source. And these blue lines would be showing you, how is water flowing toward that river and maybe possibly a reservoir there. If we had a source of contamination, such as a cattle ranch, and it could be an industrial facility, or it could be a community that has runoff, and some kind of waste was released, it could directly enter that water source and result in natural organic matter, for example, or some kind of toxins being introduced to the water supply. And natural organic matter, as Daryl will talk about in a little bit, can be associated with the formation of disinfection byproducts. If we look at general water quality pathogens, we're looking, first of all, at general quality parameters like pH and alkalinity and the chemical constituents. And we're looking at that to see how it's going to affect the downstream user. Also, we have three basic categories of pathogens that we pay attention to: uh, viruses, bacteria, and protozoa. And finally, we're looking at other factors that affect water quality. Uh, Things like we've already mentioned, water age, uh, either the precursors or the formation of disinfection byproducts. We're also looking at system materials, upstream treatment uh, methods or lack thereof also affects uh, distribution system water quality, and also our practices that we carry out within the distribution system. If we look at some of these a little bit more detail here, pH stands generally for the potential of hydrogen, and it's based on how hydrogen exists in the water. At a pH below 7, hydrogen is existing as a positive ion, and it's considered acidic. If we have water that's acidic, it can promote corrosion, which means stripping of electrons from metals. If water has a higher pH, it means the hydroxide ion, a negative ion, is predominant, and that's considered alkaline or basic, and it can contribute to things like scale formation. If we have a lot of TDS in the form of calcium and magnesium, it could end up causing scale in the insides of pipes and water heaters in the distribution system. pH levels can also affect the efficiency of chlorine disinfection, and there's often a need to balance compliance goals. For example, if we have lower pH levels, it can improve the chlorine disinfection, improved microbial control, but can also increase the likelihood of corrosion, which can give us problems with the lead and copper rule. Alkalinity is kind of related to pH. It's the resistance of a water sample to a change in pH, and it's measured by adding acid to a water and measuring the pH. And when water has a low alkalinity, it means it has a greater potential to become acidic and become corrosive. The alkalinity is considered a buffer. And so as acid is either produced, or if there's an acidic level in the water, alkalinity can buffer that and prevent it from changing the pH. And how it's measured here, you see the apparatus on the right. Basically, I'm not a lab technician, but basically you're adding acid drop by drop until the pH of the water sample is reduced to 4.2, and that gives us an idea of when all the alkalinity in that sample has been used up, and you can equate the amount of acid that's been added to the amount of alkalinity in the sample, and this is what they call titration. Hardness is another water quality measurement that can affect the distribution system. It's the concentration of dissolved minerals, and we're specifically talking about minerals such as calcium and magnesium. And this is the minerals that are directly responsible for scale development in the insides of pipes and hot water heaters. And it can reduce the volume carrying capacity of pipes, as in this image that you see here. It can also coat the insides of things like water heaters and make them less efficient, because now we have this insulating layer between the water and the metal. And generally, water over about 150 milligrams per liter of hardness is considered hard, but this here is giving us a range of 120 to 180 for hard water. And very soft water, less than 17.1, that could be associated with water that could tend to be kind of corrosive too. If we look at overall dissolved solids, this is more of a general term, which can include those types of hardness minerals, but TDS also can mean a high content of all types of minerals, like including salts. So if we had a high TDS that consists of a lot of salts, it could actually be corrosive. Now, the US EAP has a secondary maximum contaminant level of 500 milligrams per liter for total dissolved solids. And if you look at a graph here, you can see that 500 and above, US EPA's maximum contamination level is secondary. It's not a regulated. You're not going to get a fine or a permit violation, but you're probably going to get some complaints from customers. When I was uh, working in the Montana and North Dakota area, we had some neighbors that had water with a TDS of about 3,500, and it was completely undrinkable. And this was just a home, but their entire basement was a water treatment plant that included filters and softeners, and they had to treat it before it even entered the softener. And so if that TDS includes a lot of salts, that could increase the conductivity and corrosivity of water. Now, we talked about water age a little bit, but what are we talking about? Generally, we're talking about the number of days, and we could be talking about the number of hours that water remains or is retained at a point in the distribution system. And higher retention times can be caused by something like a large diameter main. One time in the Phoenix area, um, they had constructed some very large diameter mains uh, for a future development in a part of Phoenix, and I think it was a couple of 24-inch mains. However, those developments were not in place yet, so they had these large diameter mains filled with water and nobody there to really use them yet. So they were having some problems with disinfection byproducts and water quality deterioration. If you have mains that are serving areas with very low usage, same thing. And dead-end mains can have high retention times if you don't identify them and get around them and use some gentle flushing to bring in some fresh residual. You could also have a portion of the year where you have a low seasonal usage. Also, if you have short circuiting in tanks, it means that some of the water goes through the tank very fast and a portion of the water gets retained longer. We'll look at a diagram of that a little bit later. Also, we have the issue of nitrification. And this generally occurs in storage tanks when we're using chloramination in the distribution system. And so this is a two-step process where you have bacteria that first convert the ammonia of chloramines. As the chloramine ages and the disinfection residual weakens, it can the chlorine can kind of dissipate, leaving just some free ammonia. And these types of organisms, they consume ammonia as their food source. So then you have a bacteria that take that ammonia and convert it to nitrite. And then there's other bacteria that convert nitrite to nitrate. And so some of the factors are it's a system that uses chloramines or has some kind of a high ammonia level. And then the disinfection residual, if the water stays in there a long time, it declines and releases some free ammonia. And then these nitrifying bacteria consume that. Also, it's increased if there's warmer temperatures. And it can also facilitate the growth of uh, bacteria, but especially biofilm and sediments will, if the tank is not cleaned properly, they'll provide a protective environment and facilitate the growth of these microorganisms. And what you get is kind of a positively reinforcing situation where you continue to lose disinfection residual and increase the levels of nitrate. So the ultimate effect of nitrification is you have higher nitrate levels, but it also reduces the alkalinity. It uses up alkalinity, lowers the pH, the dissolved oxygen levels, and further reduces the chloramine residuals and ends up promoting bacterial growth. So now you have a situation where you have an acidic tank with toxic nitrate and bacteria growth out of control because the chlorine residual is gone. So it's a bad cycle to get into. The same kind of issues can occur at dead ends where you have high water age and you're losing chlorine residual, and that can increase the biofilm growth, the scale formation. You have increased sedimentation and increased disinfection byproduct. And you see in this diagram here, the kind of system that would have a lot of dead ends, this branching type of system. We can see various types of dead ends. Just because we see a dead end doesn't necessarily mean it's a low water use. There might be a large water use or a whole community at the end of the dead end, but dead ends that don't have any water use can cause water quality problems. There was a study done in 1996 by a gentleman, Leif Chevalier, and he's done a lot of studies with AWWA, and he found that in systems that have dead ends, that have chlorine residuals less than 0.2 milligrams per liter, it can actually, or chloramine levels less than 0.5, it can actually affect the entire system. These systems had more coliform occurrences system-wide than systems that had higher residuals at these dead ends. You see a gentleman here at the top left flushing. It looks like he's doing a full velocity flushing here, but at these dead ends, just gentle flushing to move out some of that water and move in fresh water can help a lot. And here's some of the things that can happen. One of the things is biofilm growth. So once you get biofilm growing, that biofilm can actually harbor dangerous pathogens. They can kind of hide in that biofilm layer, and it leads to a lot of other problems like corrosion. Now, this drawing is not to scale. You wouldn't have uh, scales and biofilms as thick as is shown on this image. Biofilms might be more the thickness of something like a Scotch tape or smaller. But this is just to show you what the kinds of things that are occurring. And there can be a detachment from the biofilm, and it releases sections, pieces of the biofilm that can be interacted with chlorine, and it can also float down and reestablish another growth of biofilm further on down the main in another part of the distribution system. And the growth of biofilms is actually influenced by the type of pipe material. And iron pipe is one of the problem types of pipes for biofilms, because biofilms will grow more rapidly on an iron surface. Um, and they'll have a greater diversity compared to PVC pipes. PVC pipes have less problems with biofilms. And it also can affect disinfection. For example, iron pipes can have a greater chlorine demand. And the biofilm can also work kind of synergistically with scales, and it can cause a lot of problems that impact water quality. So we'll be talking about biofilms uh, off and on with different topics that we'll be addressing today. And so some of the issues, though, that we'll talk about. So you have pipe scales that might be uh, releasing some kind of chemical, and that can be influenced by biofilm reactions, such as detachment, where they're moving those chemicals around. Biofilms can release pathogens as they disperse, and you can also have corrosion that is enhanced by biofilms. And also just increasing the overall nutrients and natural organic matter, and the bulk microbial load can be influenced by biofilm growth. And the one of the most insidious things of biofilms, it can protect pathogenic microbes from things like chlorine and even from flushing. And the kinds of topics we're going to be looking at next is the types of pathogens. We already mentioned the three types of categories of pathogens. There's bacteria, and there's an example of E. coli. E. coli 157 is the bacteria that we're most concerned with. Viruses such as flu viruses, and also protozoas like Giardia that can infect humans. So they travel in a cyst. On the far left, you can see cryptosporidium that travels through the water in a cyst form, and it doesn't come out of that cyst until it reaches a nice, warm, moist environment of the intestinal tract. Then it hatches and reproduces itself and makes people very sick. And as we're about to transition to disinfection, we think about the goal of having a negative coliform bacteria test. And we use coliform bacteria as an indicator organism. And why do we do that? We're looking at total coliform, and which includes all these other types of coliforms, different types of fecal coliforms, different types of E. coli, and of course, the pathogenic E. coli. There's two things. The presence of just coliform bacteria can mean that we have some type of contamination that's been released into the water. And that contamination could mean that we also have different types of bacteria, viruses, and protozoa. And it can also mean that we have E. coli bacteria, possibly. And a good practice is to monitor heterotrophic plate bacteria, or HPC. That gives you a good indication of the background levels of microbial activity. And in general, we want to keep our water quality below 500 CFU per milliliter. That means colony forming units of bacteria per milliliter of heterotrophic plate. Now, the heterotrophic plate bacteria gives you an idea when you're starting to have problems. You probably would see an increase in this before you had a positive coliform result. So it can give you an early warning that something's going on. There's some kind of sanitary deficiency in the system, some kind of contamination is entering, or there's there's something happening in the system that's causing some microbial problems. And the concentrations of this bacteria can depend on a variety of things. Besides just contamination entering, it can depend on water temperature, warmer water temperatures, lower residuals of chlorine, and a lot of total organic carbon, that, in other words, organics in the system can facilitate the growth of heterotrophic bacteria. And there's the units, colony forming units per milliliter, and that's something they would examine in a microscope and visually observe. And we have one poll before I switch over, and you'll get to hear from Daryl. And the question is, what is the problem caused by biofilm growth in water mains? And as you're doing that, I'm going to turn you over to Daryl, and I'll be back in a little while.
Okay, hopefully everybody has an opportunity to go through and provide their answers. Are we getting anything, Lori?
We have 82% of people have answered, and right now we have 81% saying D, all of the above.
Okay. All right, let's see what all right, the answer is all of the above. So 81% of the people are correct. Okay, so we will move on to chlorine disinfection and disinfection byproducts. Thank you, Greg, and thank you for all our participants. So why is chlorine important? So if we look at this graph here, it shows incidence or death rates from typhoid fever. And you can see that since chlorination began, there's been a steady decline. Obviously, there's a few other factors that come into play. You'd like to think that just sanitary measures in general are going to be better, but it shows the importance of chlorination. So there's three main types of disinfection, three different ways that we get disinfection. One of them is gas chlorine. You'll note that that's 100% strength. There's also liquid chlorine known as sodium hypochlorite, which is typically anywhere from 5.25% to 12.5% strength or concentration. Those come in liquid, usually plastic drums of some sort. We also have calcium hypochlorite, which is a solid. It's 65% to 70% strength. That's going to have to be mixed with water to create the chlorine. And these are commonly called pucks. So free chlorine residual in water is made up of hypochlorous acid and hypochlorite ion. This photo shows some of the bad things that can happen for a gas chlorine leak. So gas chlorine is handled very carefully. It can be very, very deadly. So a lot of systems have gotten away from it. There may be some of the larger systems that still use gas chlorine because it is very efficient and very cost effective. So I guess our fourth type, which is chloramines, is 5 parts chlorine and 1 part ammonia, and it's measured as a combined or a total residual. So chloramination is when we take our ammonia and we add it to water that's been treated with chlorine already. Then the added ammonia reacts with the hypochlorous acid and the water and forms this long-lasting disinfectant. So chloramines are long-lasting disinfectants. So from this table, we can see that we have the percent of chlorine as hypochlorous acid on the left, and we have the percent of hypochlorite ion on the right. We've got pH across the bottom. So free chlorine residual in the form of hypochlorous acid is a little bit better because it's a stronger and it has a better ability to oxidize pathogens. So if we look at our point here, we're at a pH of 7. We've got 80% hypochlorous, and we've got 20% hypochlorite. So this next graph is what I like to refer to as a breakpoint chlorination graph. And it shows chlorine residual going up on the left and the amount of chlorine that we add going across the bottom. And it's important because this helps get through the point that we need to add chlorine to a certain level in order to really have it be effective. So if we look at this, the initial stage, we're reducing compounds, they're using up the chlorine. So we're not seeing really a chlorine residual at all. We get to a point where now we're starting to produce chloramines. And so we're starting to get some benefit from the chlorine. Chloramines tend to have, that's the odor that quite often we see when we're adding chlorine to water, and we get a lot of complaints from the odors. So there's a point where we're adding chlorine and people don't really like it. Now, next we get, as we continue to add, the actual chlorine residual goes down as the organics and chloramines are partly destroyed, and we get to this point where it's breakpoint chlorination. So at that point, the neat thing about this is that from that point on, we're going to continue to get free chlorine, and it's going to be the type of chlorine that doesn't have the odor to it. It'll have a little bit, but it doesn't have the odor causing compounds in it. So it's kind of counterintuitive. The idea is that you want to get you have to go through all of this to get to this point, and then we're in great shape. We're moving everything forward, and so what you put in, you're getting out. So yeah, all the demand is satisfied, and free residual begins to build in that case. So here we're showing we've got this combined residual, we've got free residual. And the whole thing is considered our total residual. It's another case where we're actually putting some numbers to this. So say we had 0.2 milligrams per liter or parts per million used up by the reducing compounds. We got 0.3 for combined, gives us a free of 1 in our chlorine dosage of 1.5. So dose equals demand plus residual. So what dosage should be applied to a drinking water with a total demand of 0.4 milligrams per liter if the intended free residual is 1.2 milligrams per liter? So the solution, we simply add the demand in the intended residual, in this case, 0.4 parts per million demand plus 1.2 parts per million residual to give us a 1.6 part per million dose. So this is an important formula that we're going to use, pounds per day. The pounds formula gives us pounds per day when we take our milligram or million gallons per day or our flow, and we multiply that by our dosage or constant or in milligrams per liter or parts per million, and then we multiply it by the weight of a gallon of water at 8.34 pounds per gallon. Now this we're showing here that we've got a chlorine gas situation, and some of the parts with the chlorine gas, we've got the regulator, the rotometer. The rotometer is going to show what it'll provide us, how much we're applying in pounds per day. So that helps us to make sure that we're providing the right amount of chlorine in chlorine gas. All right, so let's look at this again. What is the feed rate setting for chlorine gas in pounds per day if the plant flow of 1.2 million gallons per day and the required dosage concentration is 1.5 milligrams per liter or parts per million? So our solution, we're going to take that 1.2 million gallons per day for our flow and our 1.5 parts per million for dosage into the formula. And the 8.34 doesn't change in this case because with gas chlorine, it's 100% available. So a chlorine feed in pounds per day is going to be equal to 1.2 million gallons per day multiplied by the 1.5 milligrams per liter dosage and the weight of water. So we multiply those out, we'll get 15 pounds per day. So we want to apply 15 pounds of chlorine gas per day. So now for liquid chlorine or sodium hypochlorite, our formula is a little bit different in that we're going to take our gallons per day, and that's going to be equal to the million gallons a day multiplied by the parts per million or milligrams per liter, and then multiplied by the weight of water at 8.34 pounds or pounds per day. How much? All right. And then we'll multiply or divide that. So the top gives us the pure pounds of pure chlorine if we were to actually use just chlorine. In this case, it's a certain concentration or strength. And I think we said that was anywhere from 5.25% to 12.5%. We multiply the weight multiply that by the weight per gallon, and that's the weight of liquid chlorine. So that's divided in our equation. And then you see that, so that's that formula. We're throwing some stuff in here. This SG is the specific gravity of the chemical that we're using. In this case, liquid chlorine. So if the specific gravity is greater than 1, then that means that it's heavier than water. And if it's less than 1, then that means that the chemical that we're using is lighter than water. So we'll go to another problem. What is the feed rate for 12.5% sodium hypochlorite with a specific gravity of 1.2, so it's heavier than water, when the plant flow is 0.5 million gallon a day and the dosage is 0.9 of a part per million? So we're going to throw that stuff into our formula. So we have gallons per day equals flow in million gallons per day times the concentration times the weight of water divided by the percent strength or concentration multiplied by the specific gravity and multiplied by the weight of water again. So plugging those numbers in, we have 500,000 gallon a day, 0.9, 8.34. So in this case, we convert 12.5 to 0.125. We put in our specific gravity. And we come out with roughly 3 gallons per day. So this photo depicts a chemical feed pump, and some information you can gather from it that's helpful is the max flow. So it's a little hard to read here. The max flow for this pump is 1.60 gallons per hour. So that max flow is when the speed of the pump, how fast the pump operates, and the stroke, which is either the length of the diaphragm or of the piston, how long those are, how far it is, and based off of a 100% for those. So if we want to calculate the output of a chemical feed pump, in this instance, we look at a chemical feed pump that's rated for a maximum flow of 1 gallon per hour. So what is the actual output of the pump if both the stroke and the speed are set at 70%? So the stroke set at 70%, the speed set at 70%. We're going to use this formula. We take the actual output is equal to the maximum output, 1 gallon per hour, times the percent of the stroke, which we said is 70%, times the percent of the speed, which is also 70%. In this case, we'll convert those 70% to 0.7. So if we throw those numbers in, we get a little under 0.5 gallon per hour. So that tells us that at 70% stroke and 70% speed, we're about half the maximum output of the pump. So that gives us a little bit of room either way. If we need to increase or decrease, we can lower the speed or we can lower the stroke and actually operate that pump the way it should, to the point where we need it to operate. So we've got a poll. What is the feed rate of gas chlorine in pounds per day if the water flow is 0.2 million gallons per day and the dosage is 1.2 milligrams, and that should say per liter? Your options: A, or a pound a day, B, 2 pounds, C is 3 pounds, and D is 4 pounds per day. Give people a little bit of time. Yeah, you're getting close to half, I think, of the responses. Looks like it's right around half. Well, let's take what we got here. It's looking, right now we got 68% of the people are saying 2 pounds per day, and that is correct. So if we throw our numbers into the formula, 0.2 million gallons per day multiplied by 1.2 milligrams per liter times the weight of water. And note, this is gas chlorine, so it's 100% available. We don't have to take into things such as specific gravity or anything like that. All right, so let's look. Greg had talked a little bit about the pathogen groups. You know, we have both, we have viruses, bacteria, protozoa, we've got all these different things. viruses and protozoa are inactivated. So they become unable to reproduce in essence. So that's our goal for them. Whereas bacteria are typically destroyed. So they're gone, they can't do anything. So the effectiveness of chlorine disinfection depends on a couple of things. So what's our residual concentration? What do we have out there for chlorine that's available to do stuff in the system? And the other thing is how much time has it had to affect these organisms in the system? So when we look at that, the goal for viruses is a 4-log inactivation of them. Okay, so free chlorine is trying to, what is 4-log? So 4-log is a combination of removal and inactivation that is 99.99%. That equals it basically means that you could leave 1 out of every 10,000 could remain. So what we need to look at this chart is we need to know what the pH and the temperature are. So at temperature in this case, we'll use an example of 10 degrees and a pH of 7.5, which is between 6 and 9. That gives us requires a CT of 6 milligram per liter. Okay. 1 milligram per liter free residual would require 6 minutes of effective contact time before water reaches the first service connection. What do we mean by the first service connection? So we've got this simple groundwater system with disinfection diagram. So we're applying disinfection at this point right here. Okay, because the water comes up, goes through the pump, chlorine gets added here, it goes out into the distribution system. All right, so from this point forward, what's the time of the flow in the pipe to the first service connection? So that's going to be beyond. This is the entry point. That's typically the end of the treatment plant or well house. The first customer is going to be out here, the first service connection. So we're trying to find out what that time is. So we're going to do we'll do an example problem, try to determine the CT at the first connection. It's going to be a longer problem. So we have a groundwater system that needs to achieve a CT value of 6 milligram minutes per liter at the first service connection in the system. There is a 500-foot 8-inch pipe between the disinfection point, which we go back here. Here's the disinfection point, and the first connection. Okay, so that's out there. That's the first customer that is going to potentially receive this water. And the flow is 250 gallons per minute. The free chlorine residual at that point is going to be 1.5 milligrams per liter. So if we convert the flow from GPM to CFS, so that's going to just help us work through this problem. We do that, we dividing by 7.48, that goes into our 250 gallons per minute. And we also divide it by 60 seconds per minute. And that'll give us a cubic feet per second of just a little over a half, or 0.557. Next thing we want to do is we want to get our units into inches. Or excuse me, we want to get from inches into feet. So we're going to divide 8 inches by 12 inch per feet. That's going to give us 0.67 foot of diameter for our pipe. We find the circular cross-section area of the pipe in square feet. We use pi r squared. In this case, we're using diameter times 0.785. So we do that, we plug the numbers in, and we come up with 0.35 square feet. All right. This is, like I said, it's a multi-step, it's a long process, but next we divide the flow in CFS by the area in square feet to find the volume. So if we have cubic feet per second, we divide it by square feet, we're going to end up with feet per second. All right. So we take our 0.557 CFS, we divide by our circular cross-section area of the pipe, and that gives us 1.59 feet per second. So that's the velocity in the pipe. Our next step is we divide the linear foot of the pipe, so the length of the pipe, by the velocity to find the total contact time. So if we have 500 foot of pipe and the velocity is 1.59 feet per second, we divide the 500 by 1.59, that's going to give us 314 and a half seconds. We divide that by 60, or the number of seconds in a minute, and it gives us 5.24 minutes. So now we need to know is, did we meet our CT requirements, our contact time requirements? So if we take our 5.24 minutes, we multiply by the concentration of the free chlorine residual, and we get 7.86 milligram minute per liter. So compliance is achieved because I believe we were aiming for 6, and we have more than what is required. So next, we'll talk a little bit about disinfection byproducts. What are disinfection byproducts? In this case, how do they form? So this is a simple diagram. It shows that you've got rainfall. It goes across organic materials. Quite often we'll see in those situations water that comes out, it's got tannins in it, or it's brown in color potentially. That water is taken into a treatment plant where most, but not all of the organics are removed. We can't quite, it may look like everything's gone, but quite often we can't quite get everything out. So as part of our treatment, to protect our water, we're going to add chlorine to the filtered water. But the downside from that is it's going to react with that water. The chlorine is going to react, with the organics that are remaining in the water to form these disinfection byproducts. So the water flows out of the treatment plant, it goes into the distribution system, and that's where we're required to collect our samples and determine whether we have compliance with the disinfection byproduct rule. So what are disinfection byproducts? Well, they're made up of a couple of things. One of them is the total trihalomethanes. So these are these 4 compounds. They're volatile organic compounds. They're found in drinking water. And it was determined that they pose a cancer risk if they're over the MCL of 0.80 milligrams per liter. So THMs or TTHMs they're formed in a reaction that happens between naturally occurring organic matter and chlorine. Halocetics, or the HA5s, that's 5 different weak acids that were also found to pose a potential cancer risk when those are found over the MCL of 0.060 milligrams per liter. So both the THM and HA5 compounds are the result of reactions with the naturally occurring organic materials and the decay products of plant and animal materials. So compliance for THM and HA5s in drinking water, it's determined by the locational running annual average, calculated at each monitoring location. And that average is the locational running annual average is the average of the 4 most recent quarters of monitoring data at specific locations. So we have to meet them at each one of the locations that we have out there. Some systems may only have 1 location. Others, larger systems are going to have multiple ones. So how do we prevent these things? Okay, in the distribution system, there's a few different ways that we can prevent the formation of THMs and HA5s. We can optimize our chlorine use. It's important to get the right dose of chlorine to do what we need. You want to have enough that it gets done, but you also don't want to have too much, because too much chlorine can add to the formation of THMs and HAs. We want to manage our biofilms. Biofilms can harbor things that can create THMs and HAs out in the distribution system. Adding mixing to storage tanks, or minimizing the amount of dead water in the system. Use of chloramines for disinfectant residual. Chloramines are less likely to create THMs and HAs. As Greg had mentioned before, gentle flushing of dead ends and high air retention areas, or areas where the water tends to stay for long periods. And then the last one, regular tank cleaning and water main flushing to remove debris. So if the debris isn't there, then there shouldn't be anything for the chlorine to react with in the distribution system to cause additional THMs and HAs. And then for the treatment system, if we optimize our treatment, reduce our TOC concentrations and our turbidity, that leaves the plant, then that also reduces what can happen out in the distribution system to create these things. All right. As I said, some systems use chloramines in the distribution system to prevent the DBP formation. So I think you'll find that systems that have issues with THM and HAs may move to the use of chloramines, because it does help with that. So there's a link to DBP, Disinfection Profile and Benching Technical Maintenance Guidance Manual. There's several throughout these presentations, and I encourage people to look at these. I would think that these would be documents from EPA that everybody should maintain in their library. So we've talked about flushing and water age. And so what are some of the effects of increased water age? So this study, they looked at the effects of residence time to water quality and distribution systems. And researchers found that in areas where there's low velocities or flows of water, HPC growth and the levels of THMs continue to increase with the water age, regardless of the presence of normal chlorine residuals. So even if you have normal chlorine residuals, you're still going to see an increase in the in THM formation. Typically, chlorine residuals decrease with water age anyhow. So the amount of your residuals will generally go down through time. They're also affected highly by water temperature. So on this graph, as Greg had mentioned, a CFU is a colony forming unit, and that's observed per milliliter. So as our retention time in hours went up, so did the number of HPCs that were found. And an HPC, what that does is it estimates the number of bacteria, yeasts, and mold that are in the water. It's an indicator of water quality. In this graph, we've got time along the bottom, and we've got the THMs on this side. We've got the chlorine on this side, and that shows that as time goes on, our chlorine residual decreases. So chlorine residual decreases from, say, just over 5 in this case down to just over 1, but our THMs increase from nothing, in this case, up to 160 micrograms per liter. So what effect does the storage tank have on our THM and HA formation? So the rate at which the water volume in the tank's replaced can definitely affect it. So if we were running our system, properly, we would recommend that water turns over less than every 5 days or so. But there's a balance. We want to have enough water in our storage tank to meet our peak flows. we want to have enough storage, and meet fire flow needs. But we also want to keep water at a younger or a lower age. We don't want it sitting out there forever. So we'll take an example. We have a 500,000 gallon storage tank, and our flow is around 175,000 gallons per day. So what's the turnover? So we have 175,000 gallons a day. We've got the storage tank that's a 500,000 gallon. So we'll do everything here in gallons. We're going to convert our 500,000 gallon tank over to gallons. That's 500,000 gallons, excuse me. We divide the volume by the flow. So we'll take our 500,000 gallons, we divide that by the 175,000 gallons per day, and that should tell us how many days it takes for the water to go in the tank and then come out. So that's all well and good, but does it happen that way? No, it typically doesn't happen where the water that comes in spends this ounce of water that comes in spends the same amount of time as the other, gallon of water that came in before it, or the one after it gallons. So with tanks, we have what we call short circuiting. And so we can see that the water that we put in is not necessarily going to flow, like take its time and flow through all over the place and then come out at the end. It typically, because in this case, the water that comes in is often cooler than the water that's in the tank. The new water is cooler. And the warmer water tends to be at the top, the cooler water's at the bottom. So what we find is that quite often if the water comes in up here, it sinks down to the bottom, which means it's already at the bottom and it's more likely to be pulled out and be maybe some of the earlier water that leaves the tank. So we call it short circuiting. It didn't spend its time in the tank. And we could have baffles, we could have things that move the water around. You can have whether it's an impeller or propeller in there to move the water around. You could you could put air in there to bubblers to move the water around. I know in some of the system that I oversaw, we had them put in a pipe that directed the water so that it would go circle around at least the tank and hopefully provide some mixing. So tank mixers can be very helpful to limit the amount of water age. And by limiting water age, we're hopefully limiting the amount of disinfection byproduct that we produce. So let's look at now into biofilms and what effect that disinfection has on them. So Greg had talked about biofilms. So you imagine this little film that forms on the pipe. Well, there are naturally occurring organic materials that are in the water, and there's chlorine in the water. And so those are going to affect each other. So, when chlorine and NOMs come together, they form DBPs. So there's the potential that the water that you're putting in is forming it. And then the chlorine will react with this, if there's biomass that becomes detached, that'll also form chlorines. So in a recent study, low DBP formation was observed with a chlorine residual of 0.5 milligrams per liter. When the chlorine residuals were increased to 2 milligrams per liter, however, the DBP concentrations increased sharply and then decreased after 2 weeks. So what might have happened? So chlorine can reduce biofilm growth and rate and even destroy biofilms. But it makes disinfection byproducts. So we want to kill our biofilms off, but in the process, we're likely to cause DBPs to be formed. So with a free chlorine at 2 milligrams per liter, it was effective at penetrating the extracellular polymeric substance. So that's like the layer that protects that bio mass. So at 2 milligrams per liter, which is a pretty healthy dose of chlorine, you know, you're able to get through that, you know, partially destroy the biofilm, and that, you know, that led to a period of elevated DBP formation. But I guess the goal with that is that you get an elevated level, but then through time you're able to then get rid of the biomass and move forward. So you have higher DBP formation to end up getting lower. So what effect does a pipe material have on biofilm growth? So if you look at PVC water mains, chlorine achieves a greater level of activation of organisms and biofilms than chloramine. So, you know, the thought being that chlorine is probably better, potentially better in PVC water mains. A concentration of 1 milligram per liter of either free chlorine or chloramine has been shown to reduce HBC and coliform by more than 2 log in biofilms. Now, if we want to look at iron water mains, so iron water mains, especially those that aren't coated or lined, we quite often see greater chlorine demand, and that's so with iron water mains, free chlorine residual as high as 4 parts per million have shown to be ineffective. So even at high levels in iron water mains, it may not work, and that could be to the fact that you know, especially cast iron water mains that aren't lined, you've got a lot of area to potentially grow biofilms. Now, on the other hand, a monochlorine residuals greater than 2 milligrams per liter have been shown to be successful in iron pipes. So once again, this just demonstrates the need to have the right type of disinfection for your situation. So we have another poll here. Poll 3, what are the factors that can lead to increased disinfection byproduct production and loss of residual? A, high tank turnover and excessive flushing. B, low tank turnover and sediment buildup. C, use of chloramines and system flushing. Or D, all of the above. We'll give you all a little bit of time to respond to the poll. I think we got answers coming in a little bit quicker on this one. We didn't have to do a lot of calculations, at least. Yeah, we're over half already. People flying through this one. All right. Let's see. What about 3/4? We're close to 3/4 of the way through. Okay. Well, let's look at the answer here. I can say that at this point, 59% of the people have said B, 36% all D, all the above. We've got 5% at C. And the answer is B, low tank turnover and sediment buildup. So high tank turnover and excessive flushing are going to help decrease our DBP production and increase our residual. And C, the use of chloramines and system flushing. System flushing in by itself is helpful for increasing chlorine residuals. So, and the chloramines, as we had indicated, are beneficial and, you know, on their own on certain circumstances. So, so this slide just shows. So we have Legionella is one of the things that can be of concern for water systems, and so this just shows, you know, what it might look like. Obviously, as Greg had said before, your biofilm is not that thick, but this is all just for a dramatic effect. And just to point out that Legionella is one of the things that can grow and live in biofilm. So here we're looking at the effects of free chlorine levels versus a mixed oxidant or and chlorine dioxide levels. So that this to demonstrate, you know, at the same concentrations, what's the effectiveness? So mixed oxidants and chlorine dioxide have been shown to be more effective at eliminating Legionella and reducing biofilm. So what are mixed oxidants? So mixed oxidants are produced on site by electrolysis of sodium chloride using direct electrical current in brine solution. So we've got we've got a process here where we've got anodes and cathodes, cations and anions, but we're creating a mixture of disinfecting compounds. So it's a bunch of different, you know, we've got a few different things going on here. So we've got the hypochlorite ion, the hypochlorous acid, and we've got chlorine that result from this process. So yeah, so it's helpful, and it's just another way that we can, in the right circumstance, you may find that this is the best way for you to provide disinfection, chlorination, and meet your disinfection byproduct requirements. So what different strategies out there? One study found that neither chlorine residuals nor chloramine residuals were able to control biofilm development. But when they used combination of free chlorine followed by monochloramine, the biofilms were controlled. So several factors, you got to take a lot of things into consideration when you're going to look at disinfection byproduct. And so some of those are, you know, what pipes do you have in the system? Do you have an issue with biofilms? What's your water like? What quality? How's your system designed? So we had a question about sound. Are we good?
We're still good.
Okay, thank you. So I guess I would like a word of warning that anytime you have any changes in disinfection strategy, you need to thoroughly investigate them and you need to pilot test. Any changes you should be contacting to your primacy agency, whether it's you need to get their approval or potentially you might need to get a permit. So make sure that you're not so that you don't go and do something and then regret it later. Some of the insights, one would think, does shock chlorination, does that improve the removal of biofilm? We'll just high dose of chlorine, throw it at it. Well, so the study showed that shock chlorination with liquid chlorine did not improve the impact of mechanical cleaning on biofilm removal. So it didn't help in that case. However, high velocity flushing followed by chlorination appears to be, one of the better ways to emergency disinfect water mains. So this follows in closely with the AWWA standard for when we install pipe. We always require flushing prior to chlorination. So it doesn't seem like the chlorination or initially before flushing does what we need it to do. After high velocity flushing, biofilms are significantly reduced, and the EPS layer that protects microbes from disinfection is been compromised, which allows then the chlorine in the disinfect, allows it to disinfect more effectively. Flushing before chlorination. All right. So now we're on to Greg with flushing, repairs, and emergency disinfection.
Hello, everyone, and that was a wonderful presentation, Daryl. Thank you for that. And Lori, should we take a break now?
I was just going to ask you the same question, Greg. Would you like 5 minutes or 10 minutes?
Either one is fine for me. Can we see some feedback in the chat, whether you would like to have a quick break, 5 minutes, and get done a little bit earlier, or do you need a 10-minute break? Either is fine with me. And I'm seeing a lot of fives, Lori. Do you have your timer at the ready? Oh, somebody said 10. We might have to add 10 plus 5 and make it 7.5.
Okay.
We have some we have some 10s in there. So if anyone needs a 10, um, I'll make it your call, Lori. 10 is fine with me either way.
Okay. Why don't we go ahead with the 10 and then I'll start that right now and you should be able to see the timer at the top of your browser or your Zoom window. And we'll see everybody on the other side of that 10-minute break. Okay, thank you.
Okay, here we go. Thank you for that timer, Lori. That really helps to keep us all on the same page. And did you all enjoy that presentation from Daryl on disinfection and disinfection byproducts? I I thought some of those situations and studies were kind of fascinating. And if you enjoyed that, you know, could let us know in the chat if you have questions. That sometimes we learn stuff and it causes us to have more questions than answers. So if you have questions as we're going along, you can put them in the chat, and we're all doing our best to watch the chat. And we're planning on having a dedicated portion at the end to answer questions. But if it's a pressing question that needs to be answered right away, Lori will stop us and let us know, hey, there's a question that needs to be answered before you continue on. So that's what the chat is for. You let us know, and let us know if you're enjoying the training, if you learned anything new so far. Uh, that helps to keeps a little bit of communication going, because you know we're separated by this technology. I mean, it allows us to connect from all over the country and even other countries. I saw someone joining from Canada, and there may be other countries on the line, but so we can all join together in this learning experience. Um, but we're still separated a little bit. It's not the same as being in the same room where we can just raise a hand or ask a question. So use that chat. You can also use it to network with each other, and so forth. So we're going to continue on the discussion. So we talked about the scope of distribution system water quality in the beginning, and then Daryl gave us a presentation on disinfection methods, uh, a little bit about residuals, calculating feed rates, and disinfection byproducts, and strategies to address biofilm development in distribution systems. And he mentioned at the last there about disinfection combined with flushing. And so that's part of what we're going to address now. Flushing, repairs, and even we'll do some emergency disinfection. And, you know, flushing, system flushing, we're talking about using hydrants to flush our distribution system, has a lot of benefits. And obviously it reduces the water age, maintains pipe capacity. How does it do that? Well, it gets rid of scales and biofilms, and uh, processes are ongoing to grow scales and tubercles and biofilms that could actually reduce the actual volume capacity of the pipe. And of course, it reduces biofilms and scales that are building up. I remember every year when we would flush uh, in the system that I was an operator in, we had iron and manganese, and when you open the hydrant, all that the first few minutes, all that iron and manganese would come out, and it would just be dark tea colored water coming out for a moment. And those scales wouldn't move unless you got the water velocity up high enough. So they weren't traveling into people's houses at normal flows. And of course, it'll improve the flow characteristics by getting rid of all those scales and biofilms that could reduce the flow and the flow efficiency in the pipe. Remove sediment from water mains. And of course, it's going to help us to reduce disinfection byproduct formation. And as it brings in fresh chlorine residual to dead ends, it's going to help control microbes. It's also beneficial for factors other than just water quality, because operators have a reason to get around and operate valves, make sure that hydrants are functioning. I mean, hydrants are important for public safety for more than just cleaning the distribution system. They're there to fight fire, for example. And so having an excuse or a reason to get around and operate the hydrants and valves is good. You want to make sure that everything's functioning. When we flush, we want to get up to a velocity that creates a scouring action. And you see some examples here on the left of some manganese in a pipe, some iron, slime, and incrustation in a pipe in the middle. And on the right, you can see some biofilm in a plastic pipe. You can see it's actually pretty thin. So if we get the scouring velocity up high enough, we can remove some of these items, or at least reduce them. And normally, water that's going through a distribution system is pretty slow. It's not going to move these things until you get the speed up high enough. There was a study on different types of flushing modalities, and there's more types of flushing than just the standard flushing methods that we normally use. Opening hydrants and operating valves to get the water flow going into a certain direction and get the velocity up high enough would be hydraulic flushing. We would call it unidirectional flushing. That's one of the methods. A second method is ice picking. They use an ice slurry of salt water and send that through the distribution system, and that has a lot greater ability to shear off slimes and scales in a piping system. It's a much more efficient way of cleaning. There's also this technology called air water flushing, where they inject filtered compressed air in with the water, and that increases the flow velocity of the water. And then finally, there's a system where they have ultrasonic waves. It could produces kind of a cavitation effect. Cavitation is when water rapidly changes from its liquid state to its vapor state, and it does so in a dramatic fashion. It releases a lot of energy as it goes from liquid to gas, and that can be used also to clean pipelines. So in this study, they actually found that the air water flushing was the most effective when they compared all these different methods. It was overall offered the best cleaning with the least water and the least cost. That's kind of interesting. It's not something that we normally do. This is a 2025 study, maybe something we'll see more of in the future. And the study link is at the bottom of the slide that you'll have on your handout. There's also methods of sending large sponges or kind of projectiles through the water system, called pigging and swabbing. A swab is a big piece of foam, and a pig is a little bit more rigid. It might have different types of abrasives, bristles or raised portions to facilitate greater cleaning. And you can see a kind of a 4 slides here that I took from, I snipped from a AWWA video, and I'll put the link at the bottom here on the screen. But they're inserting the pig into a hydrant, and then they close up the hydrant and they connect a pump or some kind of water force, and they push that pig through the distribution system, and it's cleaning as it goes. And finally, they have a point. They might go from hydrant to hydrant, and they retrieve it. It comes out, and they retrieve it, and those are very effective. They also have pigs, they call them, that are analytic. They can collect data about the water main on the way through. For example, some kind of acoustic testing that can determine the thickness of the main at various sections. And here's that link from that AWWA video. It's just a 4-minute video, I think, but I have the link there for you, and it'll give you some insight. And here's a image of a couple operators that are inserting a pretty large foam swab. It looks like the size of a large foam bedroll that you'd use for camping. It looks pretty big. And here's an example of a vendor's selection of different types of pigs and swabs, all different types. So it looks like that middle one with the blue top has some abrasive material on the sides. And here's an image of ice pigging here. What they do is they have kind of it's not a solid chunk of ice. It's more like an icy that you would have at a snow cone. A semi-solid ice solution in its brine. They bring it down to 24 degrees, and they insert it into an inlet hydrant here. And you can see it'll travel through the main. You got this ice pig traveling through, and you can see it sweeping away that sediment at the bottom of the pipe there. An advantage is that it's well, a couple of advantages. It's much more effective at removing sediments and biofilms. It's an abrasive chunk of ice that's going through and just scraping that main. Also, another advantage is it's not going to get stuck. These pigs and swabs, they can go through the distribution system and hit a valve or a curve or something and get stuck, but the ice picking, it'll just melt. So you're not going to have any problem with that. And so if you look at, here's an example of some water quality that was coming out, and you can see they started out getting a little bit of turbidity, and they really got a lot of sediment in a short period of time. They kept collecting samples from the output here. And that's an example of what the ice looks like, kind of an icy slurry. They make the ice in a unit on a truck, and they put it into an inlet hydrant, and they're going to plan to go to an outlet hydrant, and they're either going to send that to waste, but often they'll have a flow analysis unit, and that's helping to tell us, are we, what's the turbidity? Do we need to still keep flushing, or are we done? Do we clean the water? Upstream to the left of your screen, there's a valve that they'll open to allow that ice pig to be pushed through from hydrant to hydrant here. And then finally they'll discharge of it, maybe into a sanitary sewer. So that's ice pigging. Now, when you're using hydraulic flushing, you have this minor problem here that if you have loops, the flow can travel in multiple directions. So you put a hydrant open a hydrant at a certain location within the distribution system, and the flow, we don't know exactly which direction it's going. And so we have to use valves if we want to direct that water and get the maximum velocity for a given flow. And if we use just general flushing, meaning we just open up hydrants without using any valves, we're not going to have sufficient velocity. And we might end up just moving sediments around from place to place and not really getting rid of them completely. Now, when we use unidirectional flushing, we're actually operating valves, and the idea is to create higher velocity so we get a scouring action. So we put our hydrant in the same spot, but we close some of these valves. We're going to direct the flow so it goes in the direction we want in a unidirectional fashion so we can get maximum velocity. And we're going to start from the source and work outward and do one section at a time. So it's kind of like sweeping a large building. We start at one side and we systematically sweep. It's a good idea to start at a tank or a source of pressure. Here's a comparison between just the velocity of just opening a hydrant. We'd call that maybe conventional flushing. And you see the velocities here when we're opening the hydrant at a full 1,200 gallons per minute flow, which is high. We're only getting velocities on some of the lines like 1.2, 1.3 feet per second. That's not anywhere near a scouring velocity. The highest we're getting is 2.6 feet per second, which might be somewhat, but you see that also the sediment is going in different directions. We're not getting an efficient cleaning. Now, if we look at unidirectional flushing, we've closed some valves here, and we're getting a much higher flushing velocity. With that same 1,200 gallons per minute, we're getting 5 feet per second in this line, and it's very systematic. We're going in the same direction. All the sediment's moving in the same direction, and we're getting scouring velocity. We're going to get good flushing results from this. You probably get, like Daryl was talking about, if there's biofilm, we're taking away that biofilm's defenses by getting rid of that EPS layer. And then when we disinfect, it's going to have a greater effect on that biofilm. You can also look at some charts here. There's various charts that you can look at, and I've always just flushed a hydrant at basically its maximum flow out of the 4-inch nozzle and used unidirectional flushing and flushed until the water was clean. But the recommendations that we were looking at earlier about biofilm removal, basically the recommended velocity is around 5 feet per second, and for about 3 pipe volumes. Now this chart gives us some idea of what the minimum flow in gallons per minute would be for different diameter pipe. For example, an 8-inch pipe, to get at least 2.5 feet per second and maintain enough pressure in our distribution system, because if we opened up, 4 or 5 hydrants on a small line, and we were flushing this massive amount of gallons per minute, we could actually be in danger of losing our pressure. And we don't want our system pressure to go down below 20 psi, because that could lead to backflow events, which we'll talk about a little bit more tomorrow. But for an 8-inch line, we need 400 gallons per minute, and we can get that minimum by just opening one 2.5-inch hydrant opening. So we don't need to open necessarily the big 4 or 4.5-inch opening. We can get that amount of flushing with just a 2.5, and that would probably be more efficient for water loss control. Now we're going to do some flushing calculations here. It'll help us to get some insight into what we're doing when we flush. And let's say we have a 500-foot section that we want to flush. And of course, when you're doing a system-wide flushing, you're going to have several sections. But in this case, we're just looking at one 500-foot section of 6-inch water main. And we want to flush it at a velocity of 5 feet per second. And we want to flush an amount equal to about 3 times the pipe volume. So we're going to do some calculations here. We're going to see, first of all, how many total gallons are we going to use to flush this main? What should the flow be to attain the velocity? And then how much time will the actual flushing take? When we get it up to the velocity, how much time will it take to get those 3 pipe volumes through the hydrant? So first of all, the easiest one would be to look at the volume of water flush. And we can look at this formula here, the diameter of the pipe times the diameter squared times 0.785. 0.785 is a form of pi. It's 1/4 of pi. So instead of pi r squared, we're using d squared times 0.785. So that's the area of a circle at the end of the pipe times the length of the pipe. And then we convert it to gallons by timesing it by 7.48 gallons per cubic foot. And right off the bat, instead of showing this, we're going to say that the diameter in feet is 0.5 feet. And we can do that in our head probably, but to calculate the diameter in feet, we take the inches of the pipe diameter and divide it by 12 inches per foot. 6 divided by 12 would be 0.5. So we're going to plug that 0.5 in. So there's our It's always a good idea to draw a picture, a diagram when you're doing a math problem. We have this 6-inch diameter pipe. It's 500 foot long. So let's plug our numbers in to that volume equation. 0.5 feet times 0.5 feet times 0.785 times the length, 500 feet, times 7.48. Does anyone have if you run that through your calculator, what do you get for the volume of this main, if you're following along? Anybody have an answer? Did you bring your calculators? All right, Kirk says 734. And when I multiply that out, the decimals on my calculator look like this, 733.975, and I rounded it down to 734 gallons. That's going to be the volume of that pipe. That's one pipe volume. And we got another, and Don says 733.9. Okay, great. Thanks for the interaction. So that's our pipe volume. Now, if we look at the three pipe volumes, we take that 734 times 3, that should give us a total volume of 2,202 gallons that it's going to take to flush that main. If you could check my answer on that, because sometimes well, not just sometimes, Daryl knows, often I make mistakes. So you check me out and make sure I'm doing it right. So it's going to require over 2,000 gallons to flush this main. Now we're going to determine the flow rate. Remember, we want to attain a velocity of 5 feet per second in this main. So I'm going to do that in a separate screen here. And here's, Daryl showed us this equation earlier. We have this velocity equation that we're going to use. And a lot of times you'll see A times V equals Q. That means the area, that's the cross-sectional area of the pipe, the circular part. The area in square feet times the velocity in feet per second equals the flow in cubic feet per second. And we're going to do a little bit of variation. We're going to be solving for velocity in this case. So we're going to actually divide the flow by the area. But first of all, let's check the pipe area, and that's just the diameter of the pipe times the diameter times 0.785. So 0.5 times 0.5 times 0.785, and I didn't round that off, but I get 0.19625. If you think about it, the pipe area has about 0.2. That means if you look at the circle of that pipe from the end, it's a 6-inch diameter circle. That's about 1/5 of a foot, and that seems right to me. And if we draw a little diagram here, there's our pipe, 6 inches diameter, 5 feet long. There's looking at the end. So if we take the area now, we have the area, 0.19625, that's in square feet, and times that by the velocity, that's the velocity we desire it to go at, times 5 feet per second, we'll get the flow. And 0.19625 times 5, I got 0.9125 cubic feet per second. I still am not rounding off yet. I'm just keeping the decimals. I want those decimals to look pretty close to what you're seeing on your calculator right now. But if we rounded that off, we'd see that it's about 1 cubic foot per second. That's interesting, isn't it? So I drew this image over on the right. It's a 6-inch diameter pipe, 5 foot long. That's how much flow is occurring each second. It's almost like a volume formula, right? That much each second. Now, how much would it flow in a minute? Well, it would be 60 of these, right? And so we're going to convert it from CFS, cubic feet per second, to gallons per minute. Now, that has to have that amount of flow in that has, demonstrated or indicated, represented by that diagram I drew, has to happen 60 times to make a minute. And each cubic foot represents 7.48 gallons. So I'm gonna do that multiplication. That 0.9125 cubic feet per second times 60 seconds per each minute times 7.48 gallons per cubic foot gives me a flow of 440.4 gallons per minute. And do I have any confirmation in the chat that if you're following along with me, am I making any mistakes? Are you getting the same thing? Next equation we're going to look at is estimating the flushing time. And this is pretty straightforward. We know that the total volume we're going to flush is 2,000 202 gallons, and our flow rate is 440.4 gallons per minute. So we take that 2,000 plus gallons, divide it by the flow of 440 gallons per minute, and I get about 5 minutes. So once we get that hydrant up to full flow, we can attain that 3 pipe volumes of flushing in about 5 minutes. So that would be these would be good calculations to know about how much water it's going to take to flush and about how long it's going to take us to flush each hydrant. You know, the 5 minutes plus getting there and getting set up. You have to factor that in. Driving to the next hydrant, setting up any safety, traffic safety, and so forth. When you flush, it's important to not allow chlorinated water to enter into any streams or waterways. So you might have to have a diffuser with dechlorination on it. And these types of diffusers allow dechlor tabs to be inserted in them so that your water is dechlorinated. Calcium hypochlorite. And there's a study that was done about the effectiveness of flushing and chlorination. And they basically looked at little sections of pipe, different types of pipe, and they flushed it at a certain speed. So they had these multiple valves and short sections of pipe that they could actually remove and look at. And this study was called the efficacy of flushing and chlorination in removing microorganisms from pilot drinking water distribution systems. And that was a study when they looked at different types of pipe material and different velocities of flushing, and they looked at the effectiveness of the removal. And some things they found. They found that flushing with 3 pipe volumes and at a velocity of 5 feet per second removed about 1.5 to 2.7 log of microorganisms. But only a portion of the biofilm was removed. They found that the 3 pipe volumes at 5 feet per second gave the most benefit. And they tried different things. They tried extending the flushing up to 15 volumes, but they found there was diminishing returns in doing that. It only added a little bit more log removal of microorganisms. And remember, this is just flushing right now without the disinfection. And so let's just check here how we're understanding this, and so that what is a recommended flushing protocol among these? And I always like to add a little bit of comedy into the polls. And some of you are joining in with my comedy. I see, however, that about 80% chose answer B, unidirectional flushing at 5 feet per second or 3 pipe volumes, and that would be correct. Answer B. Now, main breaks and repairs are associated with contamination problems. There's various studies around the world, and there's plenty of evidence, of course, right here in the US. But this particular study was a household in Norway, and they looked at any time there was a situation where they had a main break or even a repair, there was about 1.6 times more incident of gastrointestinal illnesses. They looked at Sweden also. They were about 1.9 times more likely to report some kind of acute gastrointestinal illness after a pipe break or repair in the distribution system. And there's a lot of factors that contribute to this, and a lot of it has to do with trench water, like we saw early on. Trench water has potential to have fecal coliforms and all types of pathogens. And so sometimes you can have sewage lines that are roughly at the same level as drinking water. You can have sanitary sewer overflows as well. Contaminated groundwater in the trench, there could be situations where you lose pressure when you have a main break and it causes cross connection, backflow through cross connections. Also, the way we make our repairs, do we use sanitary procedures? Do we disinfect all the tools and parts that we're putting together? And also, do we follow up with flushing and disinfection of the repaired main? Those are important factors. Two most important things to maintain the integrity of the distribution system are having a continuous water pressure. If you have a loss of water pressure, it can cause contaminants to be drawn in. And the physical integrity of the distribution system. Tomorrow, Daryl is going to be teaching about sanitary surveys, and he's going to be talking about uh, the integrity of the distribution system, points in the distribution system. And of course, it's a larger topic, but sanitary deficiencies are points in the distribution system that can create pathways. And in general, the EPA has a model where contamination of the water system requires three things to all happen. You have to, first of all, you have to have a source of contamination. Now, here's a main underground. There's contaminated water around that main that has E. coli. There has to be some kind of pathway, and there's a hole in this main or a crack, some kind of maybe when the main is pressurized, it's leaking. But then we have a mechanism. We have a low or negative pressure, maybe caused by a main break or some type of outage that causes contaminants to be drawn into the main. And it can even be a small pathway that allows, like for example, something like soil bacteria to enter the distribution system. And we have chlorine there. Our chlorine residual is to provide another barrier of protection if contamination enters that. The function of that chlorine residual is supposed to be inactivation of that contaminant or that pathogen. Once we use up the residual, we don't have any more disinfecting power. After we have a repair, we want to disinfect the main. There's three basic different methods. First of all, they have a method they call continuous feed. Basically, they're getting a free chlorine residual of at least 25 milligrams per liter, and they're letting that be in the main for at least a 24-hour period. You can have a tablet main, then that is useful. An easy way to do it where you can just place chlorine tablets in the main at each pipe joint as you're installing a new main or making a main repair. And you're once again, you're aiming for a dosage of about 25 milligrams per liter. There's also a slug method where you have a highly concentrated section of chlorinated water around 300 milligrams per liter, and you slowly push it through the main, allowing about a 3-hour contact time for each section of the main. But that's a slug method. could end up having a highly concentrated chlorine. Well, any of these would have, you'd have a highly concentrated chlorine solution that's inside there, so you'd have to dechlorinate it and probably flush it to waste and make sure that no chlorinated water enters any local nearby streams or lakes. There's also some charts that can help you to figure out how many tablets, and this chart here is for 5-gram tablets. And so you can figure if you had an 8-inch main, for example, and it was 20 feet, or every 20 feet you would use 2 of these tablets. So if you're putting a new main in that's 20 feet in length, you could put 2 tablets in, and that should get you up to 25 milligram per liter dose. Now you might want to aim for a little bit higher dose in some cases if you have a lot of chlorine demand, because you want to maintain as close as you can to the residual over the time period. Now tanks, normally the easiest way for large tanks is not to try to disinfect all the water in the tank, but to spray the interior of the tank with a 200 milligram per liter solution of chlorine, let it sit for 3 hours. I've seen some methods where they do that and then they just fill the tank. And then I've seen other methods where they recommend rinsing the tank walls and draining out that and dechlorinating that water and then refilling it. And after you refill, after disinfection, you want to take a back T for all these methods, whether it's a main or that you're disinfecting or a tank. You want to have a negative coliform result before you put it back online. For wells, we want at least 50 milligram residual throughout a 24-hour period. I've found sometimes that a higher dose can be a little better. I used to use a little higher than this, about 250 milligram per liter when we would chlorinate our well, which is still less than 1% solution, but at least 50 milligrams. And you have to consider the chlorine demand. So you might want to actually dose a little higher than 50 milligrams per liter so that you can maintain the residual throughout the 24-hour period. So to do this, you want to calculate the volume of water that's actually in the casing. If you see that diagram there, you have a casing. It has a certain diameter, and there's the bottom of the well and the actual static water level. So the amount of water in the well may not be the same as the total volume of the casing. So you use that volume and convert it to million gallons. So you can use that sodium hypochlorite bleach formula that Daryl showed us earlier, and then use a 50 milligram per liter or more dose after you account for reducing compounds. And you want to hold that for 24 hours. And then at the end, you're going to pump that chlorinated water out, and you're going to dechlorinate it and then send it to waste. And then take a coliform sample of the raw water. So there's usually a sample tap on the well for raw water, and then a place where you can measure the water after disinfection. And this would be where you'd want to know the raw well water. Here's an example here. We have a well that's 10 inches in diameter, and it has a water column, total water column of 200 feet. We've already calculated, okay, the water static level to the bottom of the well is 200 feet. And we're going to calculate the gallons of 12.5% bleach needed for a dose of 75 milligrams per liter. Now, so I'm using 12.5% bleach. That would be pretty standard in the industry, and I'm going to aim for a dose a little higher than 50 because I'm thinking that some of that chlorine is going to get used up. And I'm going to also use 1.2 for the specific weight of bleach. So here's my well, 200 feet water column and 10 inches in diameter. So if I calculate the volume in gallons, first of all, I need to convert the diameter to feet. 10 divided by 12 is 0.833. I'm going to use that diameter in my volume equation. 0.833 times 0.833 times 0.785 times 200 foot length times 7.48 gallons per cubic foot will give me the amount in gallons. If I divide that by a million, I'll get my volume in million gallons. So it becomes 0.000815 million gallons. I've rounded it off from 814.9 to 815. To convert from gallons to million gallons, you can also just move the decimal place 6 places to the left. Now I can plug this in to my sodium hypochlorite formula. So there's my mg on the top, 0.000815, times my 75 milligram per liter dose times 8.34 pounds per gallon. And on the bottom, I'm dividing by that percent bleach, 0.125. I've converted to 12.5 to 0.125 decimal equivalent, times that 1.2 specific weight, times 8.34 pounds per gallon. And if I calculate that out, does anyone want to try that and let me know what you get for an answer for the number of gallons? I'll let you. I'll give you a couple seconds here to more to if someone wants to try that. But I also see that Tracy said, "Can you chlorinate too much when you're disinfecting?" Yes, you can, Tracy. You can. There's two aspects to that. You can use more than you need, and you just be kind of wasting chlorine. But also, I've heard of people going as high as like 1,000 milligrams per liter when they shock chlorinate. And what I've heard from consultants and other experts is that you can actually end up with a really high chlorine residual. You can end up kind of oxidizing the outside layer of uh, of s- of bacterial biofilms and so forth, and you're not really disinfecting what's underneath it. So yes, and I see a couple people, Olayinka and Tracy said 0.407 gallons. Let me go back and we'll look at the answer here. And that's exactly what I got. Great job. So 0.407 gallons of 12.5% bleach that we would add to that well. And here's a question here. Hole 5, what is a good general microbial test? This is kind of going back to a couple of things that we talked about earlier, kind of a little review. What's a good microbial test, general test to perform to assess water quality? And general, think of that term general. Okay, we're almost at 70% participation here, and 44% of you said E. coli tests. Well, that would be a definite indicator of water quality. If you have coliform, E. coli, or you don't have E. coli, that really would indicate water quality problems or not. But the word general, we're talking about looking at kind of what's the overall background um, of bacterial activity that's going on. And the HPC, the heterotrophic plate count, uh, would give us a good idea of what's going on overall and would help us to know when there's problems about to occur in the distribution system. So that's I've known one time I was working with a system down in San Diego area up in the mountains there, and the person who was the manager of the water distribution system was was also a microbiologist, and she often took ran heterotrophic plate count bacteria, and it always gave her an indicator when there was some kind of problem about to happen. So it provides a good general assessment of water quality. And remember, we want to, if we do these HPCs, we want to see less than 500 colony forming units per milliliter. And so we're ending up now, and today we covered some different topics. First of all, we looked at overall distribution system water quality factors. We looked at disinfection methods and calculation, and disinfection byproduct formation factors. That was in that excellent presentation that Daryl gave us today. And we also looked at some various biofilm management strategies, flushing concepts and calculation, and problems with main breaks and repairs that can lead to water quality problems in the distribution system. And finally, we looked at some emergency disinfection concepts. And so we want to thank you all for participating today and for being here. And if you want to share something you enjoyed learning about today, or ask a question, we're now open for questions. And Daryl, if you want to come on screen as well, and if you have questions for Daryl or myself, now was the time.
All right, I'm here. A little smaller than Greg.
Yeah.
Or am I big on the screen? I can't see myself.
Okay, we have a question. What is the importance of WM and hydrant flushing?
Or I wonder if that was something they enjoyed. I think that's probably,
Could be.
they probably enjoyed that because Greg asked. We also have Shelby enjoyed learning about ice pig flushing.
So no more to say about hydrant flushing, that is what you're saying.
Yeah, I don't.
Yeah, Elliot, have you seen any vendors? Have you come across, Daryl, any vendors that are contractors that specialize in ice picking?
Not I typically don't see it very much with water mains. Quite often we see it with on the sewer side, but
Oh,
yeah, because people don't, quite often it's difficult to open up a water main and to be able to do that kind of thing. So yeah, I can't say that I know of anybody that does that.
I've run across a couple of times the AWWA in Michigan and RCAP used to have what they call these field days, and a couple of the vendors, they had a truck just like we saw in the slide, and they specialized in that ice pig flushing. And so the things that you would need is that special unit on the truck to actually make the ice slurry, and then that unit where they analyze the turbidity that's coming through that kind of tells them when to start and stop. So there are contractors out there, and I see a couple more questions here. Brian Beamer said, can you talk again about disadvantages of just flushing until water runs clear in a white bucket? Well, Brian, that's a good question. The running the water, if you're unidirectionally flushing until it runs clear, um, I don't think that's a bad method. Um, until it runs clear, it might be that you use a little bit, maybe use more water than you need to. If you stick to this 3 volume pipe volume, that would be a lot more efficient use of your water. Now, just flushing by randomly selecting a hydrant, you're moving the sediment possibly around from place to place without actually getting rid of it, and you're not attaining enough enough velocity. I've tried some different methods, and at first of all, you would think that let's use a crystal clear glass and look at the water through the glass to see when it's clean. But you know what works the best? It's interesting that you used a white bucket as an example, Brian, but I found it a similar thing using a white styrofoam, like a coffee cup. You can really see if the water still has color in it. Would you like to take, okay, Kirk says, enjoyed learning about the flushing. Thank you all for today's class. Thank you, Kirk.
Chad is asking, is everyone keeping track of total gallons flushed for water loss? Probably not to the level they should be. I mean, I think it's an important thing for, or having an idea of how tight your system is. But I guess in my experience, people don't keep track of that as well as they probably should. It's definitely an important thing. Let's see.
Don, that's a good question. But I'm assuming the ice pig is encapsulated as to not add brine to the water supply. Actually, it's not. It's basically you have clean water coming behind that slug of ice, and it goes from hydrant to hydrant, and then it's evacuated out of the water system and flushed with clean water behind it, so that brine is actually washed out and probably enters a manhole in the sewer system. And Kirk says American Pipeline Solutions offers ice picking. Go ahead, Daryl. See what you see that you'd like to answer there.
So what specific disinfectants are being used and why were these chosen over other available options? So, I mean, we talked a little bit about the different, whether it's gas chlorine, liquid chlorine, solid chloramines. I mean, they're all used for different purposes. Typically, unless you have a specific situation, if you're trying to avoid disinfection byproducts or something like that, I'd say that most people are using liquid chlorine. It's generally the easiest to handle. You've got a lot less safety concerns with that than you do for gas chlorine, but it all depends on your specific situation.
Daryl, I just read something like 2 days ago, and I came across this EPA site or document. It might be one of the documents that we have in our resources, but they were having a discussion. They said, what are the characteristics of the perfect disinfectant? And one of the things that they said was that it would be a disinfectant that you could measure the residual, and it would last throughout the system, and it wouldn't add any objectionable byproducts, and it would be easy to handle and cost effective. And some of the things you were just saying, the ease of use and the cost effectiveness, and plus all the benefits that you discussed in your presentation about some disinfectants were superior at different specific needs in a distribution system, I think goes along with that. Jacob says earlier you mentioned ultrasonic waves being used to create cavitation. Is this method being used, and what are the concerns about pipe pitting from cavitation? Yeah, that is a new technology for me, Jacob, and I can if I didn't share the link in the slide, I can send it to you. If you send me an email to gpearson@mtu.edu. I'll share both of our emails, in fact, in this next slide here. But that's a good point. I assume that it's a controlled form of cavitation where it's not so heavy that it's actually going to damage the pipe. but just enough to dislodge the sediments and biofilms. But I assume that's a new technology for me, but I assume they have to be very be careful when they use that method. Do you see Wendell's question there, Daryl?
Yeah, yeah, I guess I'm not sure. So if it's specifically uranium is being introduced in the distribution system, because I would think that uranium was, if it's coming from the source, flushing isn't gonna affect the concentrations of uranium unless you're getting it in the distribution system. I can't say that I've had a lot of experience with systems that have uranium issues. But
I remember one system that I was talking to in Southern California, and they had uranium, and they were looking at different solutions. I think they were looking at ion exchange. It was a special type of ion exchange unit, and of course, reverse osmosis would be a solution, but that would be a lot of wasted water, right, Daryl? But you'd lose a lot of if you have a low amount of water production to begin with.
yeah,
You'd
I
lose
guess
some.
I guess my point here is that flushing isn't going to do anything unless it's introduced somehow in the distribution system,
Yeah,
because the rate, flushing, I wouldn't think would affect that concentration.
so uranium's a source water
Typically, yes.
treatment problem. I'm going to go back here tomorrow. Uh, Everybody come back tomorrow, same time, same day. We're going to be looking at corrosion control in the lead and copper rule, cross connection control, and Daryl is going to be sharing Daryl is intimately familiar with sanitary surveys and sampling and monitoring. So don't miss tomorrow. Bring all your questions and comments, and bring your calculators. And Jim, tomorrow's survey, there's an evaluation component, but it also helps you to confirm that you attended, and you need to do it to get your certificate. It's a little process that they use in the CTT to get your certificate. It kind of confirms if there was a compliant, if there was a certification agency that wanted to confirm that you attended. We'd have that survey to say yes, they attended. Is that correct, Lori?
That is absolutely correct. And I'm going to drop that reminder right into the chat so you can see it. And I will also share again the files that we shared today in case you didn't grab those yet. One is going to be the reference file, which I actually didn't drop yet. So don't worry if you don't have that one yet, you're about to. And then the slides. Thank you everybody for your great questions. Thank you, Greg and Daryl, for all the awesome information. It's clear with all the questions that it was very valuable information. And we're excited to see everybody back tomorrow. Please use the same Zoom link that you used today. We tried to make it easy. And here are those references. If you have any questions or that you want us to answer tomorrow, you're welcome to let us know those as we start tomorrow too. And you're already registered for tomorrow if you are on the list for today. So you don't need to do anything extra.
All right. Thank you, Lori.
Yeah, thank you guys. And thank you, Ingrid, for holding down all the IT things in the background too, for helping us.
Yes.
We got a good team going. So thank you, everybody. And we'll kind of hang out here for a few minutes. If you have any problems getting any of the files open or anything, I'll hang out for a few minutes. Nobody else needs to, but just know that maybe 4 or 5 more minutes here, we'll keep the session open. Otherwise, we'll see everybody tomorrow.